So, stoichiometry is really a pretty simple concept when you get right down to it. It's a mean-sounding word in chemistry, but it's little more than the process of using coefficients. Those would be the whole numbers we put in front of our products and reactants in order to balance a chemical process. And we're going to use these coefficients to determine relative amounts of reactants and products that we will need and produce in a certain chemical reaction. So we always start any stoichiometric problem by balancing the equation, make certain that it's balanced. And because propane has 3 carbon atoms in it, and the only product that contains carbon is carbon dioxide, and there's only 1 carbon atom in each carbon dioxide, we're going to have to produce 3 CO2s. Likewise, because there are 8 hydrogens in a propane molecule when it gets oxidized by oxygen, if it produces water containing all that hydrogen, and there are 2 atoms in each water molecule, you're going to get 4 water molecules as a product. Now that we know our products contain 6 oxygen atoms in the CO2s, because we have 3 of them and there are 2 in each, and because there's only 1 in each H2O, 4 more in the H2Os, we need 10 oxygen atoms. And of course, since each oxygen molecule contains 2, we're going to need 5. So we have a balanced chemical equation. Now, what this means, literally, and here's the stoichiometry part, is that 1 molecule of propane is going to require 5 molecules of oxygen for it to be completely combusted. And when we're done, we're actually going to end up with 7 molecules. 6 are going to become 7 because we're going to get 3 carbon dioxide molecules and 4 water molecules. Now, the same that is true of molecules is true of moles, because after all, a mole is just a great big number of molecules, 6.02 times 10 to the 23rd of them to be specific. So if we had 1 dozen propane molecules reacting with 5 dozen oxygen molecules, it means the same as 1 mole of propane molecules would react with 5 moles. What you have to be careful of is not to mistake moles with mass or numbers of things with amounts of things, because these are not amount ratios in terms of mass. These are not ratios telling us how much. Simply, they're ratios telling us how many. And therefore, I can prove it by showing a propane molecule has a molar mass of 44 grams per mole, so a mole of propane would be 44 grams. Likewise, if oxygen molecules are 32 grams per mole and we need 5 of them, we're going to need 160 grams of oxygen for this reaction. And the products we're going to get are 132 grams of CO2, and we're also going to end up with 72 grams of water, because after all, 3 times 44 grams per mole is 132, and 4 times 18 grams per mole is 72. And clearly, this ratio of masses is not the same as the ratio of the molecules given by the coefficients. For instance, if it's really a 1 to 4 mass ratio, 44 times 4 would be around 170 grams, and we only have 72 grams. So it's imperative that you realize that you should never use these ratios on masses, but always on moles. And one thing that is significant before we do a problem is we do obey the law of conservation of mass, namely my 2 reactants add up to 204 grams, as do my 2 products. We don't lose any mass in the process. We just rearrange these molecules. We change them. Now, as an example problem, if we have 20 grams of propane that are burned in excess oxygen, that means you have all the oxygen you could possibly need, how many moles of each product is produced? And so simply, I'm going to start with the mass of propane that we begin with. And knowing full well that I have to use moles, not mass, for these relationships because I see that for every 1 mole of propane, I should get 3 moles of carbon dioxide. My first goal is to convert propane into carbon dioxide. And the molar mass of propane is 44 grams per 1 mole. And so consequently, quick conversion, I'm dealing with moles, which is a necessity when I'm doing stoichiometry. Now for the stoichiometry part. The equation tells me 1 mole of propane results in 3 moles of CO2. And so they're essentially equal, and I can make a conversion factor out of this stoichiometric relationship. 1 mole of propane is equivalent to 3 moles of CO2. Everything cancels, and I'm left with my answer, which would be moles of CO2. In this case, 1.36 moles of CO2. No problem. If instead I had wanted to do how many moles of water are we going to get, well, I could back up to this point right here, because the only difference is the stoichiometric ratio. Instead of being 1 to 3 as it is with carbon dioxide, it's 1 to 4 for the water product. So I would say 1 mole of propane is equivalent to 4 moles of water. And yes, I get a different answer, namely my product is 1.82 moles of water. However, these two are fairly simplistic questions. Just make sure I start with moles and I get my moles. But rarely do we deal with moles. Typically speaking, we deal with masses. So let's look at a second problem then. This one gives us the reaction between aluminum and iron 3 oxide, which produces aluminum oxide and iron. And in the two parts of the problem, we want 13 grams of iron 3 oxide to completely react, and we want to know what mass of aluminum is required. Then we're going to want to know what mass of aluminum oxide is produced or results from the reaction. Now, as with the previous problem and all stoichiometry problems, the coefficients in the balanced equation are critical to getting the right values. So I'll take the time to first make sure my equation is balanced and see right off that it is not, because I only see 1 aluminum atom in the reactants and 2 of them appear in the products. We can't just create atoms out of nothing, so we have to start with at least 2 aluminum atoms if we want 1 formula unit of aluminum oxide produced. Then the oxygen is balanced, I notice. We have 3 on each side. But since we start with 2 iron atoms, we have to end up with 2 iron atoms. This is a correctly balanced chemical equation. So I can now answer the question. If 13 grams of CO2, or excuse me, iron 3 oxide, I don't know why I was thinking CO2, are reacted, what mass of aluminum is required? Well, I do know this, that for every mole of iron 3 oxide, I'm going to require 2 moles of aluminum. So to do the stoichiometry, I first must make a conversion to mole. So now, first a conversion to moles. And if I look at the formula of iron 3 oxide, 2 iron atoms and 3 oxygen atoms add up to 159.6 grams per mole. 159.6 grams iron oxide per 1 mole of iron oxide. The mass of iron oxide cancels and is replaced by a mass or moles of iron 3 oxide. Now the stoichiometry magic, so I'll pick a different color to highlight it. Here's where our relationship comes in once we're talking about moles, because for every 1 mole of iron 3 oxide that I consume in this reaction, I'm going to need 2 moles of aluminum. The rest is easy then, and the rest is not stoichiometry. Just because the question wanted me to instead get a mass instead of moles, I just make the conversion again from moles to mass, mass to moles. And 1 mole of aluminum, given the atomic mass of 27, is 27 grams of aluminum. And everything cancels, and I'll be left with a mass of aluminum in grams. And when I break out the calculator and plug these values in and round to 3 digits, I get 4.40 grams of aluminum. So yes, we need far less aluminum, even though we need twice as many atoms, because the mass of aluminum is so small compared to the mass of iron 3 oxide. For the second part of the problem, I'm going to start the same way. I'm going to start with the mass of iron 3 oxide, and I'm going to convert to moles because these relationships are molar. They are not based on mass. 159.6 grams of iron 3 oxide. The only difference here is my stoichiometric ratio is going to be different because it's a 1-to-1 ratio between the iron 3 oxide and the aluminum oxide. So yes, 1 mole of iron oxide being consumed results in the production of 1 mole of aluminum oxide. Moles of iron 3 oxide cancel and are replaced by moles of aluminum oxide. Now, same was true in the last problem. Simply because we were asked for a mass, we can quickly do the conversion, and 1 mole of aluminum oxide is equivalent to 102 grams of aluminum oxide, resulting in 8.31 grams of my product, aluminum oxide. As a final example then, we could jazz it up a little bit more. For the combustion of hexane, how many molecules of oxygen are required in order to produce 20 grams of carbon dioxide? First, the balancing. 6 carbons requires the production of 6 CO2s. 7 hydrogens, or 14 hydrogens, requires the production of 7 water molecules. And a grand total of 6 times 2 is 12, plus 7 is 19 oxygen atoms. We need 19 halves of an oxygen molecule. It's 19 halves times 2 is 19. Of course, typically we like whole number ratios when we balance our equations. It's unnecessary when you're doing stoichiometry because the ratio will stay the same anyhow. But if you want to double everything and get whole numbers of 2 to 19 to 12 to 14, that's fine. But we're going to do the problem the same way. We want 20 grams of CO2. And we want to know how much oxygen we need to get that 20 grams. Well, I see the relationship is 19 to 12 between oxygen and carbon dioxide. So first I need moles, and 1 mole of CO2 is the equivalent of 44 grams of CO2. Now we can make the conversion between product and reactant in this case, because the relationship clearly tells me that we get 12 moles of our CO2 produced for every 19 moles of oxygen consumed in the reaction. There's the stoichiometry, and that's essentially what I needed in this problem. At the end, I just jazz it up because I'm asked for a number of molecules. I just use Avogadro's number relationship because 1 mole of anything, including oxygen molecules, is Avogadro's number of those molecules, in this case, of oxygen. And I've converted from a mass of a product to a number of molecules of a reactant. And the final answer is 4.33 times 10 to the 23rd molecules of oxygen required. So you want to get yourself 20 grams of CO2, you're going to need that many molecules.